Hello. So we are now up to our Venn diagrams video. So what are Venn diagrams? Venn diagrams are simply a way to visualize set operations, meaning union, intersection, complement, and difference, those set operations. So how does Venn diagrams do this? So first of all, we use circles to represent sets. So anytime you see a circle in a Venn diagram, it's a set. Except we use a rectangle for the universal set. So that one is different. And then we use shaded areas to represent the elements in a set or part of a set. Or I should use the correct word, subset of a set. Okay, so this is how Venn diagrams does this. So first, I'll show you a situation where we have a universal set and two sets in that universal set. So the rectangle stands for the universal set. This circle I will call set A, and this circle I will call set B. Now, this would be what I'm about to show you is the visualization or the picture of A union B. Union means all together, all the elements in A and B all together. So I would show this by shading everything in A and B. I'm going to show you 4 of them right now, so I'll go ahead and draw all 4. So in every case, the rectangle is the universal set, the left set is A, and the right side is B. Okay, in the second one, I want to show A intersection B. So in that case, I would shade only this part, because that's these elements in this shaded area. These are the elements that A and B have in common. Okay, in the third one here, I want to show the complement of A. Complement means everything in the universal set that is not in A. Not in A. So I definitely don't want to shade anything inside this circle because this is what A is. So I will shade outside that circle, everything outside that circle. That is the complement of A. And here I want to do A minus B. So I want to shade all the stuff that is in A but not in B. So that would be here. Anything that's in this shaded area is in A, remember this is A, but is not in B. I can't shade this area here in the intersection because some of that stuff, or all of this stuff in the middle here, is in B. Okay, I can also use Venn diagrams to express more complicated expressions. like expressions that have two or more set operations, such as this one, the complement of the intersection of A and B. Okay, so for more complicated expressions, I advise using a numbering system to simplify matters. So every region in this diagram is going to get a number. So I'm always going to call the complement of both sets, the outside. I'm always going to assign number 1 to that area, and then I'm going to give this the region 2. I'm going to give the intersection 3, and then this part I'm going to call it region 4. Okay, so now I go to the set operation notation, and just like in the past, we're going to do the inside of the parentheses and write down here what we get. So A intersection B gives me region 3, right? So region 3 represents all the elements in here, in the region. Okay, so I've done the inside of the parentheses. Now I need to find the complement of 3. So the 3 also acts like an element. So the complement of 3 would be, what are all the things in the universal set that are not 3? Well, 1, 2, and 4, right? Those are the elements in the universal set that aren't 3. So then, in the end, 1, 2, and 4 is the result. So I shade regions 1, 2, and 4. And I shade carefully so that the only region that's not shaded is region 3. Okay, let's try this again with another expression. This time the complement of A union B. Okay, I'm going to number my regions 1, 2, 3, and 4. Alright, so order of operations, I do this first. The complement of A would be everything outside of A. So not 2, not 3, 1 and 4. And B is everything inside this circle, 3 and 4. And now I just union these two. 1, 3, 4. So now I shade 1, 3, and 4. Being careful to avoid shading any part of region 2. Okay, done. Now, it gets a little complicated when you have 3 sets inside your universal set. So I'll draw what it looks like first. So I need to make sure the rectangle can handle 3 sets. And the 3 sets must intersect each other like this. It might take a little practice to get used to drawing that. So the rectangle is still the universal set. The names of my sets are now A, B, and C. And now I have more regions to worry about. Okay, So when I have 3 sets, the numbering system is different. Well, this part's the same. The outside is 1. This part's the same too. 2, 3, 4. But I still have more. This little region is region 5. The very middle is 6. This is 7. And down here is 8. So there should be a total of 8 regions if you drew this correctly. And I always number it the same way. So you might need a little practice drawing it a couple times and numbering it the same way. That way, when you're talking about a certain region, like region 6, you always know where that region is in your picture. My 6 is always in the middle. So try to be consistent. Try to be consistent. Okay, so let's try to find this. A union B intersection C. Okay, there are no parentheses. So we just move left to right. Order of operations, left to right. Which means I will do this first. The A union B part. So A union B means I keep all the elements that are in A and B all together. So this would be 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, now I will intersect what I just found with everything in C. C is 5, 6, 7, 8. And then I just look for what they have in common, which is 5, 6, 7. Oh, but there's more to do, so I shouldn't put that yet. Hold on. Oh no, that is the whole thing. Sorry. I thought I had more to do, but that's it. So it is 5, 6, 7. And so I shade 5, 6, 7. So it's just this little area that ends up getting shaded. Okay, let's do one more with 3 sets. A, B, C, and then my numbers 1, 2, 3, 4, 5, 6, 7, 8. This time I'm going to do the complement of A intersection B, and then intersect that with C again. Okay, so first inside the parentheses, A intersection B, that's just 3 and 6. Then I do the complement of 3, 6, which is 1, 2, not 3, 4, 5, not 6, 7, 8. Now C is 5, 6, 7, 8. I remember that from before in the other problem. And now I do the intersection of these two. 5, 7, and 8. Okay, I just double checked and that's correct. So now I can shade 5, 7, and 8. So 5, this time I do not shade 6, I shade 7, and I shade 8. Okay, so stick to the numbering system at least at the beginning because you're just starting out doing this. And you can keep doing the numbering system for as long as you're doing Venn diagrams, but if you in the future think you don't need the numbering system anymore, you can do it in your head, then go ahead and do it in your head. Just don't do that at the beginning. Don't try to do too much in your head because it's a little risky. Stick with the numbering system until you get to a certain comfort level. Okay, last thing about Venn diagrams is going backwards. And by going backwards, I mean if I give you something shaded already, can you tell me some set operation notation that'll match this picture? So can you think of a set operation notation that would produce this picture? Can you do it in that direction? So the numbering system might help us here. So we're back to two sets. So the numbering system is just 1, 2, 3, 4. So you can see that region 4 is shaded. So I'll write that down. So region 4 is shaded. And we know some things about region 4. Region 4 is part of B. So we know 4 is part of set B. We know something else about 4. We know 4 is not part of A. So it's part of B, but it's not part of A. So we know that whatever the notation is, B has to be in the notation, obviously. But not all of B, right? Because region 3 is part of B, but that's not included in the shaded region, so we don't want all of B. Well, there's some ways to remove part of a set. One way is to use difference. You use the minus. That can remove part of a set. You can also use intersection to remove part of a set. And that's a little harder to think of. So, and I want things to be a little harder in this case. So, I'm going to say not allowed to use the difference operation because that just makes it too easy. So not allowed to use difference. Okay, so we have to use intersection if we're going to remove part of a set. So if I take set B and I intersect it with something, then I can remove this part of B. And that something is complement of A. So let me tell you why it's complement of A. So we have set B, but I only want to keep this chunk. So to keep this chunk, I intersect B with the stuff that is not in A. Because remember, 4 is part of B, but is also not part of A. So these are the two characteristics of region 4. Part of B, not part of A. So what do I do to get region 4? I intersect those two things. Because 4 is part of B, it is also not part of A. So that is exactly what this says. All the elements that are in B and at the same time not in A. That's why this notation matches that picture. The shaded region is in B but not in A. This tells me all the elements that are in B but not in A. Same thing. Okay, last thing I'll do is give you the picture for something that has 3 sets, and we'll come up with the notation. A, B, C, number my regions, 1, 2, 3, 4, 5, 6, 7, 8. The middle one is 6, sorry. And the shading is 3, 6, and 5. 3, 5, and 6. So 3, 5, and 6 are shaded. So what do we know about this region? Well, if I look at 3, 6 here, 3, 6 is the intersection of A and B. And if I look at this, 5 and 6, 5 and 6 is the intersection of A and C. And this final shaded region is just the union of 3, 6, and 5, 6. This final region is 3, 5, 6, right? So I simply have to union this with this. So I take the intersection of A and B and the intersection of A and C, and I union them. And there I have it. This matches that Venn diagram. Okay, this last section, it's harder than what I just previously discussed. So if this part was hard to understand, don't worry. We will definitely go over this in class. I hope that the earlier stuff in this lecture was much easier than this part for you. Okay? See you later. Bye.